Hello students, welcome to EPG Pathshala. I am Vidya Kothekar from All India Institute of Medical Sciences, where I was teaching biophysics for over 32 years. I had been head of biotechnology bioinformatics at JP Institute of Information Technology and also been the director of D.Y. Patil Biotechnology Bioinformatics Institute in Pune. But my real introduction is I am a teacher and teaching biophysics for more than 45 years. Today, I am going to talk about a module which describes electromagnetic radiation and its interaction with the biological systems. This is from the paper Techniques Used in Molecular Biophysics, Part 2. After completing this module, you should be able to understand the basic concepts and the parameters related to electromagnetic radiation. You should also know hydrogen spectrum and other spectral series like Balmer Series, Rydberg formula, and there are a number of spectral series that you will be knowing. You would also know the relationship between the atomic structure and the electromagnetic spectrum using both classical as well as quantum mechanical approach. You will be also introduced to quantum mechanical approach for non-hydrogen like atoms and also some molecules. We will discuss interaction of electromagnetic radiation with biological systems in general. And then this will be followed by use of this interaction in various biophysical techniques which are based on either absorption or scattering of electromagnetic radiation by an object, tissue, or a cell or anything. As you know, light rays have both electrical and magnetic properties. That is why it is called electromagnetic radiation. There are a number of research techniques in biophysics which are based on the interaction of electromagnetic radiation with the biological objects, any kind. They might be small solution type objects, there might be cell suspensions, there might be some reflecting solid reflecting surface, and like that. These techniques nowadays are of great importance in understanding biomolecular structure, their functions, and interaction amongst the biomolecules, and the mechanisms related to the biomolecular interactions. Basic concepts of electromagnetic radiation. Historically, EMR originated from study of dispersion of light through a prism. It has characteristics of both waves as well as particles, as proposed by Albert Einstein in 1905. EMR consists of synchronized sinusoidal oscillations of electric and magnetic fields. The electric field is shown by blue color and magnetic by red color. These are at right angles to each other and perpendicular to the direction of the wave propagation. These waves travel at the speed of light, 3 into 10 to the power of 8 meters per second inverse, and are characterized by the velocity c, wavelength lambda, and frequency nu. The c is distance traveled per second, wavelength is the distance between the two adjacent peaks or troughs, and nu is the number of waves traveled per second. What are really spectral lines? Everybody talks about spectra and spectral lines. But the spectral lines are some dark and bright lines on the otherwise uniform, continuous spectrum or a medium, maybe black or a white or other different medium, and they come from the absorption or emission of light within the substance, and that's why you see them as different lines. How were they discovered? They were discovered by the passing of electric current through the hydrogen gas. The hydrogen gas was taken at low pressure, and when the electric current was passed through it, the tube glows with the blue light. But after passing that blue light through a prism, what one observes? One observes number of lines, dark and bright. These are small bands rather. In the case of hydrogen, there are 4 prominent bands at 656.2 nanometer, which is a red line, 486.1 nanometer, which is a blue-green line, 434 nanometer, which is a blue-violet line, and 410.1, which is a violet line. Who discovered it? It was Max Planck. He was the person who first gave that why the lines should be discrete, rather, why they are not a continuous blue or green or like that, rather. So he explained that the spectral lines must have something to do with some discrete movements, rather. So he explained this in terms of resonant oscillators oscillating at different frequencies. It was a concept that he said that these resonant oscillations have something really to do with these lines. And because this is a discrete number of oscillators, the energy should be quantized, that you will find 1 or 2 or 4 or 6, like that, not a continuous band. Then, because there was no direct linkage, on one side hand you have got spectral lines, and other hand you are talking about the oscillators. What is the relationship? It was Albert Einstein who, in the year 1907, was the first time he said that the light behaves as a stream of bundle of packets of energy, which is also quantized, and that's why you see it as discrete different lines. Albert Einstein proposed that light was composed of photons, which are small discrete bundles of energy epsilon, which is proportional to its frequency nu, given by epsilon equal to h nu. The proportionality constant h is a Planck's constant, having value 6.626, 10 to the power of minus 34. And epsilon is equal to h upon 2 pi multiplied by twice pi into nu, or it can be called h cross omega, where omega is the angular velocity and h cross equal to h upon 2 pi. The frequency nu and wavelength lambda are related by the relation nu lambda equal to c. Louis de Broglie, in the year 1925, showed dual character, wave nature and particle nature, is not possessed only by radiation but also by all atomic particles. And he described the wavelengths of moving particles of mass m and velocity v, which is given as lambda equal to h upon mv or equal to h upon p, where v is the velocity of the particle and p the momentum. Number of scientists tried to understand the relationship between the frequencies of different spectral lines emitted by hydrogen atom. First in this list was Johann Balmer. In the year 1885, he described spectral lines of hydrogen in the visible domain by a simple empirical relationship given below. Here, m is equal to 2 and n has to be always greater than m. Swedish physicist Rydberg gave a formula in 1888 to describe the wavelengths of spectral lines of many substances and different series. 1 upon lambda as per his rule equal to rz square 1 upon n dash square minus 1 upon n square, and r here is called the Rydberg constant 1.097 into 10 to the power of 7, but n always has to be greater than n dash. Then later on, Lyman at Harvard proposed another series to explain hydrogen spectrum in ultraviolet region, and this could be given by Rydberg formula for n dash equal to 1. Later, number of other scientists, Paschen, Brackett, Pfund, Humphrey, discovered series for n dash equal to 3, which overlap with the Brackett series discovered later in 1922 for n dash equal to 4. Pfund series for n dash equal to 5 was discovered experimentally. Humphrey discovered a series for n dash equal to 6 in 1953, and so on. And we give in this table the wavelengths for different series in the case of hydrogen atom. Understand what is really a spectrum, how does it originate? One has to understand the atomic structure, and then only we can find the relationship between the electromagnetic spectrum and the atomic structure. The first attempt in this direction was done in 19th century by J.J. Thomson. That time he just proposed an atomic model. He suggested that atom was a sphere of positively charged electricity with protons in which there were electrons. They were added so as to neutralize the positive charge of the proton with the negative charge of the electron. So the whole atom by itself is neutral. Then naturally people could not say how the positive and negative charge live together and how it is stable. So the first atomic model really was proposed by Rutherford, and he was doing some studies on discharge through the gases, and then he just suggested that atom has a central positive charge nucleus, but the rest of the atom is almost empty, so you don't see anything. So if there are electrons, then they are either surrounding or clouding around the nucleus and not so visible. So when he did Rutherford scattering experiment of alpha particles, is very famous experiment rather. So he found that time that that whole atom is almost empty, that nucleus is very small and electrons are only clouding around that nucleus. But then this was also not, because from the mass and charge and whatever values they had at that time, this was not a complete picture. The picture got completed after the discovery of neutron in 1932 by James Chadwick. He discovered a neutron and completed the atomic structure. He said that it has nucleus with protons and neutrons. and they're bound together not by electrostatic force but by strong nuclear force, and electrons are orbiting around the nucleus, and the neutron has the mass almost same as proton, whereas it has no charge, so it is neutral. The first model which really correlated the spectrum with the atomic structure was basically extension of the Rutherford's model by Bohr. That's why it was called Rutherford-Bohr Model. It was Niels Bohr in 1913. He modified Rutherford's model. This model was also based on Planck's quantum theory of radiation. And he suggested that electrons in atom orbit the nucleus, same as Rutherford. But electrons can orbit the nucleus stably without radiating any energy. And these orbits are called stationary orbit. And only certain discrete distance they have from the nucleus. The rule 3 of the Bohr model shows that the orbits have definite energy, and in these orbits electrons acceleration does not result in radiation and energy loss. Electron can only gain and lose energy by jumping from one allowed orbit to another allowed orbit, and which is shown in this picture, which explains the various spectral series we discussed earlier, like Balmer series, Paschen series, how the electrons jump from one energy level to another. Let us see now how the frequency of the emitted radiation is connected to the atomic structure. This was done by the Bohr model. He said that absorbing or emitting electromagnetic radiation always has a frequency nu, and this is determined by the difference in the energy levels, and it is governed by Planck's relation delta E equal to E2 minus E1, which is the difference in the energy levels, equal to h nu, where h is the Planck's constant. Thus, the frequency of the emitted radiation at an orbit of period t is given by classical mechanics as a reciprocal of the classical orbit period nu, or nu equal to 1 upon t. What is the importance of Bohr model? The significance of the Bohr model is that the laws of classical mechanics are applied to the motion of electrons, but only when restricted by quantum mechanics. And the Bohr model could determine energy spacing according to the rule 3 given in the Bohr model, and came to exact correct quantum mechanical rule that the angular momentum L is restricted by an integer multiple of a fixed unit. L is equal to n h upon 2 pi equal to n h cross, where h is the Planck's constant. N are the number of shells, n equal to 1, n equal to 2, n equal to 3, and these are called the principal quantum numbers, and they define these shells. And H cross, as we have seen, is equal to h upon 2 pi. The Bohr model is important because it was able to calculate the energy of all the allowed orbitals of a hydrogen and hydrogen-like atoms. The lowest value of n equal to 1 gives the radius of the orbital, which is equal to 0.0529 nanometers. This is very commonly known as the Bohr radius. What is de Broglie wavelength? The force condition that angular momentum is an integer multiple of h cross was interpreted by de Broglie as a standing one wave condition, like mv square upon r equal to z ke e square upon r square, or energy of each orbital is given as z ke e square upon 2r, and the electron is held in a circular orbit by balance of centripetal force and electrostatic force. Arnold-Sommerfield extended force model to explain fine spectrum. Orbitals, he said, are not circular but have elliptical shape, and this gives a major axis and a minor axis describing orbital or azimuthal quantum number. And when the k decreases, the orbitals become more and more elliptical. So we show in the picture the elliptical orbitals with same energy and quantized angular momentum. Origin of quantum mechanical approach lies in Heisenberg's uncertainty principle. Sigma x into sigma p should be always greater than h cross by 2, where sigma x and sigma p are standard deviation in position and momentum. The atomic spectra of hydrogen-like atom, however, can be understood on the basis of Schrödinger Equation, which follows de Broglie principle. If Zd be the nuclear charge, Z being atomic number, of the atom or ion, and E the charge on the electron moving around it, the nucleus at a distance r, its potential energy V would be equal to minus z square upon r. Schrödinger equation in this case can be written as minus h cross square upon twice me del square minus z square upon r psi equal to E psi, or H psi equal to E psi. I won't go into the details of this Schrödinger equation, but the equation can be solved in polar coordinates r theta phi, considering the wave function made up of three separate things: a radial part which is dependent only on r, angular part which is dependent on theta, and azimuthal part which is dependent on phi. The wave function is then written as r of r, theta of theta, phi of phi. Again, I won't go into the solution and how we arrived at the final results. And it gives us basically three equations as shown here because of the applying the condition of variable separation. And then there are restrictions. So m and beta are constants, but beta can be replaced by L into L plus 1, and where L is always greater than equal to real value of m. And the solution generates three numbers: n principal quantum number, L orbital quantum number, and m magnetic quantum number. And the most important thing is the solution of Schrödinger equation in case of hydrogen atom gives the same energy levels as given by classical mechanics. I won't go into the details of the solution or any further details, but tell that this principal quantum number, orbital quantum number, and magnetic quantum number are the crux of the electronic spectra of hydrogen and hydrogen-like atoms. The question is, the quantum mechanical approach based on the Schrödinger equation and using a radial kind of function, radial and angular kind of function with the variable separable method, can it be extended to atoms which are non-hydrogen type? That means these atoms which have more than one electron outside the shell. In hydrogen-like atom, we assume that the nucleus and the electrons in the closed shell are taken as one body, and only the valence electron outside it should be one. Then it is called a hydrogen-like atom. In other atoms, there might be 2 electrons, 3 electrons. Question is, can we really extend it? The answer is complicated. The Schrödinger equation methodology cannot be directly extrapolated to a non-hydrogen atom without evoking several approximations. These were given by Hartree, Hartree-Fock, Hartree-Fock-Slater. They used antisymmetric product of wave function. Then they tried to use self-consistent field theory method and tried to solve it for the non-hydrogen type atoms rather. How do we go to molecules from it? Because molecules have several nuclei and the electrons, it's like a cloud in between them. So it's a non-centrosymmetric system. So again, you cannot extend that approach further. But a combination was done by Rutherford. He started with the LCAO approximation, that is linear combination of atomic orbitals. So that was his starting wave function. And then again he used Fox or Hartree-Fock equation, or it is called Fox equation only, and then used self-consistent field theory method. Again there was a problem that what do we use for atomic wave functions? There are several ways rather, like the classical using Slater type atomic orbitals, which can describe the shapes of atomic orbitals properly. But then you cannot calculate all the integrals needed in Rutherford's equation and Fox equation and like that. There are several integrals, two center and multi-center integrals are like that rather. So people who use ab initio framework, they use simple exponential orbital as a starting wave function for the atom. And other people, they restricted themselves to the use of number of electrons. They took valence electrons, some people took only few valence electrons, and there was a series of methods based on that. I won't go into their details, but there are methods like C-NDO, complete neglect of differential overlap, I-NDO, intermediate neglect of differential overlap, MI-NDO, again another neglect of differential overlap, and several more methods were there. Electromagnetic spectrum, as shown in the left picture, is a term. It's a collective term used for connecting all wavelengths that we know. Only they are different wavelengths and frequencies. These are all transverse waves which propagate through vacuum, and the properties depend on the wavelength or frequency. We just show the properties of different waves or wavelengths in the electromagnetic spectrum in this table. Gamma rays, which originate from nucleus, X-rays, which originate from atoms, vacuum ultraviolet, which originate from molecules, and again UV visible, again originate from molecules, infrared, H bonding, Raman scattering, and microwave rotation of the molecules. How does electromagnetic radiation interact with the matter? Here, we show a sample, a suspension of some molecules in green color. The incoming light is shown I0 by black color. Then, the part of it, A, can be absorbed by the sample. Part R can be reflected with the angle of incidence equal to angle of reflection. Part S can be scattered, like goes in different direction. Then can be also internal scattering in the sample. And part T is the transmitted part. In solid samples, very often the beam does not come out. It may be completely attenuated at a very small depth. But total intensity of the incoming light I0 can be put equal to this absorbed component, reflected component, scattered component, and the transmitted component. How does electromagnetic radiation interact with the matter? When the radiation comes, part of it gets absorbed, part gets reflected, part gets scattered, goes in different direction, and some part gets transmitted. Now, this depends upon the properties of electromagnetic radiation as whether it is monochromatic or polychromatic, synchronous, that is starting at the same time, or asynchronous, that is starting time of each wave is different. Plane polarized, that means the end of the light vector describes a plane only. Circularly polarized, the end describes a circle. And elliptical polarized, that it will lie on the surface of a ellipsoid. Now, the interaction with the biological samples very often in biological tissues depends on the wavelength of the incoming radiation. Sometimes electromagnetic radiation may get totally attenuated. This is because of the scattering and absorption, and it deposits all its energy to the absorber. But how much it will penetrate depends, and where will it deliver its energy depends on the permeability constant mu0 and the wavelength lambda of the incoming radiation. It characterizes the distance after which the intensity will become, if it is I0, it will become I0 upon E. The biological effects of EMR can be understood at the whole body or tissue level. These are very, very important, because that is the potential safety and health hazards of the radiation due to cell phones, microwaves, radio waves, TV broadcasting, everything. It all depends upon how much energy is really deposited at a particular tissue or particular organ or like that. And EMR has plethora of applications because of this. In medical imaging, therapeutic appliances for physical therapy, non-invasive delivery, bone healing, list of applications. I can't list all of them here. If you go to the molecular level, then at the molecular level, the light can be scattered, elastically scattered, or it is called elastic scattering. It is very important for X-rays, because if the X-rays are scattered, then they can give rise to constructive or destructive interference because of the difference in the path length and phase difference, which is caused by the electronic structure of the molecule. And structural analysis of any biological molecule uses X-ray diffraction. It is one of the biggest and the most important area of the biophysics. Spectroscopic techniques, that is based on the absorption or reflection of electromagnetic radiation. Absorption of ultraviolet, visible and infrared light by biomolecules is very important for studying biomolecular interactions. Use of light scattering in biology. Inelastic and quasi-elastic light scattering can be used for studying molecular weight, size, diffusion constant, association and dissociation constant, dynamics, etc. We show in this picture on the left hand side the scattering of light through the object suspended in solution. The upper one is a bigger object, lower one is a smaller object, and the scattering can be measured by instrument. At theta here in this equation given by Rayleigh depends on the angle of incoming and scattered radiation. Alpha in this equation is polarizability, r the size of the particle, and lambda the wavelength. So by measuring theta, we can calculate the size of the particle, and if we monitor it, we can study the dynamics. Inelastic or Raman scattering, that the outcoming beam comes of different energy, that means different frequency and wavelength. This phenomena originally proposed by Semyakov in 1922, but experimentally observed by C.V. Raman and K.S. Krishnan in 1928. The emitted light can have lower energy or higher energy depending on the phenomena, and these are called Stokes or anti-Stokes line, and they are extremely useful for analyzing vibrational spectra, which are normally difficult to be done using the UV spectroscopy. So, students, let me now summarize what we have learnt in this module. First, we tried to understand basic concepts about electromagnetic radiation, and electromagnetic spectra are explained. Then we tried to describe different series, spectral series, by giving Rydberg formula, describe Balmer series, Paschen series, Brackett series, Pfund series, and Humphrey series. We explained you how atomic structure and energy levels came using classical as well as quantum mechanical approach. We discussed interaction of EMR with cells, tissues, whole body and molecules, and we enumerated few biophysical techniques which are based on EMR. We discussed use of scattered radiation, scattered electromagnetic radiation for the study of size, shape, dynamics and vibrational energy levels of biomolecules. Thank you very much.